Everybody, this is our lesson on rates of reactions, and by the end of this lesson, you should be able to explain the factors that affect the rate of reaction, such as temperature, concentration, particle size, and the presence of a catalyst. So first, let's talk about reaction rates. So reaction rate, or rate itself, is defined as how fast or slow a reaction will take place. And this really depends on the complexity and the number of bonds within the reactants. So the more bonds they have, the more energy it's going to take to break those bonds so that they can form the products, or the more complex it is, the same issue. Your formula for rate is equal to negative change in reactants over change in time. So we have to look at the negative change in reactants because we know that change is calculated as final minus initial, where you start out with 100% reactants. And over time, as those reactants change to product, your amount becomes less and less. So you're going to have a smaller number subtracting a large number, which is why we have to have that negative out front to kind of counteract that, because we cannot have a negative rate. And for a reaction to occur, particles must have enough kinetic energy, so they have to hit hard enough, and then proper orientation, they have to hit the right way. So as you can tell in this little GIF over here, you see these particles are hitting each other, but only when they hit the correct way are they able to form a bond. So now let's talk quickly about the factors that affect reaction rate. Our first one is concentration. Remember, those brackets mean concentration. And if you increase concentration, that'll lead to an increase in collisions because you have more particles present in that amount of space. So more likely they will hit each other the right way, which will increase the rate. Temperature, because if you increase temperature, that is directly proportional to kinetic energy, so you're making them move faster, which will then result in more collisions, which will then result in an increased rate. Particle size. So this one's a little different from what you might consider here. So if you decrease the particle size, you will increase the surface area. So if you grind your compound down into a powder, you're increasing the amount of surface area exposed, which then allows for more collisions, which increases the reaction rate. And then also a catalyst, which is what we see over here on the GIF. This will speed up the reaction by lowering the activation energy. So it actually offers an alternative pathway for the reactants to get to the products. You still start the same and end the same, but you have a different pathway that requires less energy. I compare this to when you go to a theme park and you know that there's like a height limit for a ride. A lot of people can't ride those, but then if you go to like a ride that's in the kiddie section that has a shorter height limit, more people can ride those rides. Kids and adults can ride. So a catalyst is a lower height restriction so that more particles can get through the roller coaster, as you can see here. And we look at a couple spots, and we'll kind of look at these on the next chart as well. But the first one you need to know here is called activation energy. And this is the energy needed to go from reactants to products. So in this little GIF, it's that peak of the hill here, okay? So your catalyst will actually lower that hill, which means more particles can go through. The species that is available at the top of the hill, so at the top we are completely breaking bonds and starting to form the bonds of the products. So that is called an activated complex or a transition state. And then in the body, we have catalysts as well, which are known as enzymes. So here is two different forms. Let me kind of get my mouse out of here. We have two different forms of what are called potential energy diagrams, and we have an endothermic and an exothermic here. So as you can tell too, this one is up here, the little GIF is labeling spots for you, and I'm going to kind of go over them on this first one here so you can see it. But in the first one, as you can tell, this one is from beginning to end, you see that the products line is higher than the reactants, which means the products have more energy. When the products have more energy, that means it was absorbed in the system, which means this is endothermic. If the reactants have more energy than the products, then energy was ultimately given off, which means that it would be exothermic. So a couple values to know here as we're looking. This arrow here is known as the energy of your reactants, because from baseline to where the reactants are, that's how much you start with. And then the one over here is your energy of products. The one all the way up to the peak of the hill, that's the activation energy of the forward. And then the one from the peak of the hill and from products to the peak of the hill is the activation energy of the products, or the reverse reaction, because that's how much energy you would need for products to go back to reactants. And then the change in energy here is the overall change. This is known as the heat of the reaction, and it would be positive because ultimately we gained energy there. So if I were to say that we started with 5 joules of energy and you needed 15 joules of energy to go through the reaction, that means you need 10 joules, because you already have 5, you need 10 more, okay? So that's just a quick, brief way, and we'll go over this in class if we have questions of what these look like, but just a quick view. Pause the video here if you want to copy that stuff down.